Good morning, everyone. Thank you all for coming. First of all, I apologize for the delay. I was visiting a very cool lab in this institute and I just completely lost track of time, so sorry about that. Uh, Once again, we'll be having two lectures today. The first one about cake cutting. So let's get back from the indivisible mode to the divisible mode. Uh, Let me just quickly remind you about, just jog your memory about some of the stuff that we did yesterday. So we were talking about dividing a resource called a cake. Someone doesn't like cakes. Uh, which is this continuous 0-1 interval among n agents, and the preferences of these agents are given by evaluation functions, and we made certain assumptions like non-negativity, additivity, and such. We defined a bunch of fairness notions called proportionality, NV freeness. We talked about the existence of proportional NV free allocations, talked about finding such allocations in certain specific situations. Today we are going to sort of sink our teeth a little deeper into one of the fairness notions, which is NV freeness. Yesterday we talked about NV freeness, two algorithms for NV freeness. One was, okay, why don't people remind me of the algorithms for NV freeness that we talked about yesterday? Algorithms for NV freeness, cake cutting. Anybody? I cut you choose for 2 players and for 3 players? Trimming one, the Selfridge-Conway procedure, right? So we talked about 2 algorithms. So let me just write those down. So we looked at the I cut, you choose. This was for 2 agents. We looked at Selfridge-Conway for 3 agents, and I sort of hand waved about what happens for more number of agents. So we talked about the Brahms and Taylor protocol, which works for any n, but there was an issue. What was the issue? Yeah, it was a finite protocol, but it was an unbounded protocol. There was no bound purely in terms of n that you could specify on the number of queries. And that also talked about a development by Aziz and McKinsey, which gives a bounded protocol. Okay. Now, except for the first one, a common feature for the other ones is that sometimes players might end up getting disconnected pieces of the cake. So like some part from here, some part from there, some part from there. Okay, and sometimes the pieces are like really tiny, so you can get a lot of crumbs, which is not great. Right? Ideally, you would want a single contiguous piece of cake. Okay, so that's going to be our focus for today. Okay, so we are going to revisit the cake cutting problem, but we are going to put this constraint that every player should get a connected piece, no crumbs allowed. Okay, so this is cake cutting with connectedness. Okay. Now, a very natural question that one might ask at this point. So by the way, the objects that we'll be talking about today look like this. So this should be the piece that goes to agent 1, then this should be the piece that goes to agent 2, and so on. Now, here's a natural question. Which is, does there always exist a connected NV free allocation of the cake? And the answer to this question is yes, it always exists. And the first proof of this fact that I know of is by Stromquist in a paper from 1980, I think. So that's great. The object that we are looking for always exists. So what's the next natural question? How do you find it? So this question was, I think, posed in this paper, if I'm not wrong. So it was open for a very long time. No one solved it. So Stromquist solved it himself. And the answer is that there is no finite protocol or algorithm. This is from a paper by Stromquist again. This is from 2008. By the way, these references you can find on the web page for this lecture series. And if anyone is unable to find me, please send me an email. If you're not able to find my email, ask me. So this is a bit disappointing. No finite procedure can find a connected NV-free allocation. Okay, so the idea is that you can cook up, again, weird sort of evaluations such that any procedure is sort of damned to, run forever. Okay. So what do we do now? We make approximations. Okay. So we are going to sort of lower the benchmark. The question that we are going to ask today is, do there exist algorithms for finding a connected but approximately NV-free allocation? Okay. And I'm going to deliberately withhold the definition of approximation here. We will see what it means when I give you the result. Okay. But it is some sort of approximation. And the answer to this question will be yes. Okay. So that's the first part of today's topic. Any questions so far? All right. So before we get into the algorithm, oh, by the way, yes, and this is from a paper by Francis Su from 1999, and it will so happen that the algorithm is also going to sort of give as a corollary the existence result here. So we'll get another proof of this fact. Anyway, before we get into the algorithm, here's a very useful combinatorial result. How many people have heard of Sperner's lemma? 1, 2, 1.5, okay. Okay. How many people have heard of Nash equilibria? Okay, more people, okay. So there's a very intimate connection between Nash equilibria and Sperner's lemma. After the lecture, go find out. Okay. So on the face of it, this lemma has got nothing to do with cake cutting. It's got to do with triangles. Say there's a triangle T. And we start by dividing this triangle into smaller triangles. You can call them elementary triangles, or the technical term is baby triangles. for those who are looking for formal terms, we are working with a simplex, and this division is called a triangulation of the simplex. Okay, but triangles are special, very special kinds of simplices, so I'll just call them triangles today, and I'll just work with these very nice, elegant looking divisions of the triangle. Okay, and you can make this division as fine as you want. You can just subdivide each thing and okay. Uh, so that's one thing. You start with a triangulation into elementary triangles. There's another component that Sperner's lemma needs, which is that we are going to assign labels to each of these vertices here. Okay. So that assignment of labels to each of these vertices has to obey two conditions. That labeling is called Sperner's labeling, and it comes with two conditions. The first condition is that the main vertices should all have distinct labels. So 1, 2, 3. Okay. The second condition concerns the vertices on the boundary here. It says that the label of any vertex on the boundary should be either 1 or 2 for this edge, either 2 or 3 for any vertices here, either 1 or 3 for any vertices here. So any vertex on the boundary should inherit the label of one of the extreme vertices. Okay, so here's a Sperner labeling. Everybody happy so far? Nothing very fancy going on. And as for the internal vertices, assign them any color you want. Doesn't matter. 1, 2, or 3, doesn't matter. Okay, so this is a valid Sperner coloring of the triangulation that we created. Now Sperner's lemma states that whenever you have a triangle that is subdivided into such triangles and that is labeled in a way that is consistent with these conditions, there always exists a baby triangle that is fully labeled. By fully labeled, I mean that has all the 3 labels, 1, 2, and 3. And you can see that there's one here. Okay. In fact, the lemma says that there's always an odd number of such fully labeled baby triangles. In particular, there's always at least one. And the proof of this lemma is super elegant, so we'll do it. And the proof comes with a story actually. So think of this entire entity here as a house. Someone doesn't like a house either. So this is a house. These things here are rooms, these little baby triangles. And think of all the 1-2 edges, these 1-2 mini edges, like this, as doors. So let me mark those. Did I miss something? Yeah, I missed something. Did I miss something now? Yes. And one more. Okay, I think I've got all the doors here, right? So all the blue squiggly lines are the doors. All right. So a couple of observations to start with. The first observation is about the doors on the boundary edge. Okay. So look at this boundary edge here, the 1-2 edge. I claim that there's always an odd number of doors on the boundary. And the reason for that is quite simple. Think of in your heads as moving from the point 1, the label 1 here, to a label 2. It will be clear in a moment when we get to the main proof. Yeah, there's a reason I'm calling them doors, because we're going to walk through them. But let's just look at the number of doors on the boundary. Start walking from this label 1 point to the label 2 point. Okay. So you know that when you start, you start with label 1. When you end with label 2. So there's at least one 1-2 switch. Yes. And if it so happens that there is a switch from 2 back to 1, then there has to be another 1-2 switch to compensate for that. Right? Any further switches are paired up. Okay. So number of boundary is odd. That's one. The next observation is about rooms. So what are the number of doors that a room could have? Can a room have 0 doors? It can. What kind of rooms have 0 doors? It cannot have 0 doors. Look at the picture. So for example, here's a room that has 0 doors, right? It has no 1-2 edge in it, right? It could be all 2s, all 1s, all 3s, or maybe 3-2-2 or something like that. Okay? There can be rooms with 0 doors. Can there be a room with 2 doors? I see a nod. I see 2 nods. I see 3 nods. Why? Someone should tell me. What kind of rooms have 2 doors? Just a little bit louder. Yes. So think of a triangle with 1 on the top and 2 and 2 on the bottom. So it has 1, 2 and 1, 2 doors. Or flip 1 and 2. So there's a 2 at the top and 1 at the bottom. Right? Can a room have 3 doors? Why? You cannot have 3 doors, right? Okay. What about rooms with 1 door? Exactly. Can there be a room with exactly one door? Yes. What kind of rooms are those? Those are the things that we are looking for, right? Those are the fully labeled elementary triangles. Great. So a room can have 0, 1 or 2 doors, no more, and with one door is exactly, it's an if and only if, is a fully labeled elementary triangle. Fantastic. So the object that we are looking for is a room with a single door. Now let's get to why we are calling them doors and rooms and house. So say you're on the boundary somewhere and you start walking into the house from one of the doors. I'm going to require you to walk in a way that when you enter a door, one should be to your left, so one should be here, two should be here, to your right. Okay? That's your entry door. So for example, you can enter through here. Okay? It's going to be a proof by walking, so just pay attention to this. So say we enter a room from a 1-2 door, and we know it exists because of our observation number 1. There's an odd number, so there's at least one such door. So this is a well-defined step. You enter through that. So you enter a room. Now that room can have either 1 or 2 doors, because it certainly has a door. You use it to enter the room. If that room has only one door, you can go home happily. We have found the room that we are looking for, right? Otherwise, what? Otherwise, it must have 2 doors, and you can happily exit the room from the door. Correct? Now you're in a different room. You have already consumed the door of that room. Once again, it can either have one door, in which case go home. If not, there has to be another door through which you can exit the room. Keep going. Now such a path will either end up in a fully labeled triangle, or you might be thrown out of the house via one of the doors, right? Note that you cannot be thrown out of the house from here or from here, because Sperner coloring forbids any 1-2 edges here. There cannot be any doors here or here. So if at all you are thrown out of the house, it has to be over here. Everybody happy so far? Okay. Let's go back to observation number 1. The number of doors on the boundary is odd. Suppose it so happens that because after you enter it, you go around for a while and you are thrown out, then the entry and the exit are paired up. Can everyone hear me still? Okay. Is this recording? Okay. Okay. So for such a walk that throws you out of the house, the entry door and the exit door, you can think of them as pairing them up. And by observation number 1, there has to be at least one more door. From observation number 1, there has to be at least, oh, by the way, can everyone still hear me okay? All right. So the entry and exits are paired up here, and because of observation number 1, there has to be at least one more door through which you can re-enter, right? Maybe you're thrown out again, but again, because the number of doors is odd, there should be yet another door through which you can re-enter. Okay? Which means what? Yes. So one of these walks is bound to run into the object that we are looking for, right? That argument is almost foolproof. There's one more ingredient that we need to prove, which is that such walks cannot cycle back on themselves. And try to think about what happens. Can you re-enter a room? Is it possible to re-enter a room? Every room has at most one entry and at most one exit. So when you re-enter it, think of the first room that you re-enter, right? It has to be through its dedicated entry, but you must have used it to enter earlier, which means you must have entered the adjoining room even before, so it cannot be the first room that you enter, right? It's a proof by contradiction. Bottom line, there is at least one walk that will take you to the fully labeled elementary triangle. Questions? Okay. I hope people can complete the proof now. I'm not going to write down the whole details. There's one additional piece of worry that we need to be careful about. So the way I've written the lemma here, it only says that there exists at least one. So the proof I gave to you works for at least one. But say you want to prove that there exists an odd number of fully labeled elementary triangles, you need one more argument for that, for situations like these. So don't worry about the other labels. But okay, fine. Let me just put this thing here so that you believe me. You can complete this to be a valid Sperner labeling. Okay. The interesting bit here is that there's these two fully labeled elementary triangles, and none of them can be reached by a walk from the boundary. Okay. But the interesting bit is that they can be reached from one another, like that. Okay. So the same proof with the additional argument that any elementary triangle fully labeled that is not reachable from any of the boundary doors has to have a path to another elementary triangle. So such unreachable elementary triangles are paired up. That gives you the odd, this is somewhat of a stronger implication that there's an odd number of fully labeled triangles. Okay, but we won't be needing the oddity today. We'll just need the at least one implication. All right. Questions? Okay, so that's Sperner's lemma. What does this all have to do with cake cutting? So the arguments that I'm going to outline from here are actually due to Forrest Simmons, but I don't think he wrote it up for publication at any point. So his ideas were popularized in Sue's paper, Francis Sue, the 1999 paper. I strongly recommend reading Sue's paper and also Stromquist's papers. Very readable, very enjoyable, a lot of fun. Okay, so cake cutting. So recall that a cake was this very dull 0-1 interval for us. And there was a set of agents. and we defined a notion of fairness called NV freeness, which simply meant that NV freeness meant that an allocation A is NV free if for any pair of players I and J, this condition holds. And like I said, today we are going to be concerned with the connected NV free problem. So let's start with the simple case of only 3 players. And whatever I say generalizes to any number of players, but I don't want to complicate things. I think the three agents case is sufficiently interesting. Let's try to look at the geometry of all the cuts, all the connected divisions among 3 players. So here's the cake. What could a connected division of this cake among 3 players look like? Forget about NV freeness for a moment. It simply means that you cut it at 2 points and each piece has some length, say x1, x2, x3. Think of these as variables that you could play around with. So if I have to draw the space of all the connected cuts among 3 players, it's captured by this. Right? 3 non-negative variables that sum up to 1. So let's try to draw this. And that's why I'm working with 3 players, because I want to draw things. So one extreme point would be 1, 0, 0. That means x1 is 1, x2 and x3 are 0. Then you could have x1 equals to 0, x2 equals to 1, x3 equals to 0, and 0, 0, 1. Okay, these are the 3 extreme divisions in which some player gets the entire cake and the other 2 players get nothing. And everything else should be somewhere in between. And if you think about it, that space looks like this. It's a hyperplane that cuts the 3-dimensional coordinate system at these 3 points, and you only look at the non-negative part of it. Okay? Note that every point here on this chopped up hyperplane corresponds to some connected cut of the cake and vice versa. This completely captures the space of all the cuts that we're working with. So although that figure that I drew is in 3 dimensions, the space of cuts is actually just a 2-dimensional object. Yes? And that object is what? Anyone? It's just a triangle, an equilateral triangle, right? My drawing might not suggest that, but it is an equilateral triangle. And these are the extreme points. Yes? And we're hoping that one of these points is actually NV free, or at least approximately NV free, and we can find it. Okay. So let me just specify the assumptions on the valuations or the preferences of the agents that I'm going to make. And they're actually somewhat more relaxed compared to the ones that we made yesterday. The first assumption is that given any cut x1, x2, x3, so this simply indicates the lengths of the pieces. I'm going to assume that every player can answer the following question: which is your favorite piece of these three? Okay, so I make this cut in the cake, and I ask one of the players, tell me which is your favorite piece, and they point to that piece. Okay. That's a pretty benign assumption, I think fairly uncontroversial. The second thing that I'm going to assume is that the players are hungry, which means that any player prefers a non-empty piece over an empty piece. Okay. So now that we have a triangle and we are experts on Sperner's lemma, we are going to try to invoke Sperner's lemma somehow. For that we need like an intermediate setup. So I'm going to keep this figure here. I'm going to copy it because I need a reference labeling. So note that this is the triangle on which we are going to invoke Sperner's lemma on, but there's like a side copy I need to do something else. So again, these correspond to the 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm going to triangulate this space, so just like we did in Sperner's. And the same triangulation is also done here. Now for each vertex of this triangulation, instead of assigning labels, I'm going to assign owners. Okay, so let me give those players some names A, B, and C. Sorry? Arbitrary. So we can make it as fine as we want, and that will give us better approximation, which I haven't defined yet, but we'll see in a moment. Yeah. All I need is that these two triangulations are identical. Okay, so I'm going to assign ownerships, not labels, ownerships to each of these vertices such that every elementary triangle has all three owners. And watch how I do it. Okay. So I'm deliberately being a little bit coy about giving you an algorithm for finding a way of assigning distinct owners to everything. I'll just say that, trust me, there is. For now, here's your triangulation, very nice and symmetric, and here's a way to assign owners. Okay, if you want details, go ahead and read Sue's paper and the references in that paper. Okay, but I don't want to get into those technicalities. Anyway, what does it mean to be an owner? Here's what it means. So our algorithm is going to go to a vertex and ask the owner of that vertex, which is your favorite piece at that cut. Okay? So this cut means that, so the first piece is like length 0, and the third piece is length 0, and everything is for the second piece, right? That's what this cut point means. Now, if you ask the owner, namely player A, which is your favorite piece among the three, what is A going to say? We have made this assumption that players are hungry. Given that the other two pieces are empty, A is going to say that it likes piece 2, right? So let's number the pieces geometrically from left to right as 1, 2, and 3. So A is going to say, I like piece 2. That answer is going to serve as a label for this triangle at this point. Fine. Let's go to a different main vertex. Ask the owner, agent C, which is its favorite piece. What should C say? 1. Add a 1 here. This has to be 3 now, right? What about these points here? What do we know about the cuts on this edge? So, right, so note that for any of the points on this edge, the first coordinate is 0, meaning the first piece is 0, meaning that whatever they answer, they're not going to answer 0. They're not going to answer 1, right? The answer is going to be either 2 or 3, right? I don't know what they like, but it has to be either 2 or 3. This is looking nice, isn't it? What about this edge? Here the third coordinate is 0, so answer is going to be either 1 or 2. Yes? Okay. Now what should I do? So you have a triangle which is triangulated. It has labels that respect the conditions for Sperner's lemma. So, I mean, it would be ridiculous if we don't apply Sperner's lemma. So let's apply Sperner's lemma. That means there is some colorful or fully labeled baby triangle. Yes? Okay. What does it mean in the context of cake cutting to have a fully labeled elementary triangle? Exactly, great. Note that I ensured the property that for any of these baby triangles, the owners on the 3 different vertices are different, right? And maybe it looks like this. So at this cut, agent A prefers piece 1. At a nearby cut, agent C prefers piece 2, and at another nearby cut, agent B prefers piece 3. So what we have is not a single cut, but 3 sort of nearby cuts, depending on how fine this triangulation is, at which different agents prefer different pieces. Now it would have been nice had there been a single cut at which 3 agents preferred 3 different pieces. That would have been envy-free, right? We don't have that luxury right now, and that's why the approximation. So it's not an approximation in the sense of preferences. Remember yesterday we talked about this epsilon EF where the epsilon was subtracted from the valuations. This is an approximation in the geometric sense. There are three nearby solutions where you can have NV-free like things going on. So use Sperner's lemma. What we are guaranteed is that a set of three nearby cuts. I'm using the word nearby very loosely because I haven't defined the notion of nearness yet. But at least in terms of pictures, there are three nearby cuts where different agents prefer different pieces. Now you can imagine making this triangulation finer and finer, and you will have increasingly nearby cuts where you have NV-free like things happening. But there's something else we can do with this. There's a little more juice that we can squeeze out of it, which is to use convergence properties. Okay, so you use some triangulation, you guarantee something else, you make it even finer, maybe somewhere else you are guaranteed another colorful triangle. Keep on making these things smaller, they can be arbitrarily small. If the valuations are closed, okay, topologically, then the limiting cut has to be NV-free. Okay, I'll define what closed means. So by the way, this is what I mean by an approximate NV-free division. NV-free connected division, by the way. So note that connectedness is ensured by our construction, right? By making a third assumption on the valuations, we can actually prove the existence as well. So let's make a closeness assumption. So I'll need some notation. So any point in this space is a three-dimensional entity, x1, x2, x3. Let me call it some capital X equals x1, x2, x3 to denote this tuple. And think of a convergent sequence of a bounded sequence, a sequence of cards. Okay, so some x1, x2, x3, and going on and on. Each xi here is a point here, has its own x1, x2, x3s, and this is just an infinite sequence of cards. Now this is a bounded sequence. Yes? Because we are working with this space, so it cannot spill outside this space, right? So any such infinite sequence is a bounded sequence. What do bounded sequences have? Convergent subsequences. So are people familiar with the Bolzano-Weierstrass theorem from analysis? Anyone who's not familiar with it? Oh, a lot of people are not familiar with it. Okay, wonderful. Then you can ignore the closeness part. The idea is that there is a limiting cut where we can turn approximate NV-freeness into exact NV-freeness. This is just a formal way of saying that. So the assumption is that valuations are topologically closed, which means that for any sequence x1, x2 up to xn, if at each of those cuts player I prefers say piece 2, okay, at this cut it prefers piece 2, at this cut it prefers piece 2, then at the limiting point as well it should prefer piece 2, okay. So the preferences are closed under limits. That's all I'm trying to say here. If prefers piece k at each of x1, x2 and so on, then prefers piece k even in the limit. Okay. So if the valuations are closed, then you can take increasingly finer triangulations. They'll all converge to a single point, and at that cut, all three agents will prefer different pieces, and life will be good. Okay. So this is a convergence-based result. So this is not giving you an algorithm because it has this like infinitely many things that you'll have to do, and you cannot hope to have an algorithm because Stromquist told us so. There's no finite algorithm for exact connected NV freeness or connected exact NV freeness. Okay, so that's so much for cakes. I'd like to get to the second part of the topic, which is rent division. This is very much like cake cutting. Oh, and by the way, so there's something I did not mention. So Sperner's lemma, the way I proved it, was only for triangles, but there are higher dimensional versions of Sperner's lemma as well. So it holds in any dimensions, and because of that, you can use it for any number of agents in the context of NV free cake cutting. Okay, so everything I say holds for any number of.
Can you connect the two notions of approximation by here we had epsilon, right?
We can, yes. So yeah. So say your valuations are varying smoothly. Okay, they're not very jagged. They're varying smoothly. They have some Lipschitz properties. Then geometric closeness also implies that the preferences don't jump by much. So you can treat that as your epsilon. More questions? All right, so rent division. So here's the problem. Again, for 3 agents, everything goes for more number of agents, but say there are 3 friends who are looking for an apartment with 3 rooms, and that apartment comes with a monthly rent. Okay. Just like any self-respecting mathematician, I'm going to assume that the rent is 1. That's a total rent for all 3 rooms put together. Now, these friends are facing the following problem. They have to figure out who gets which room and how much rent he or she pays for that room, such that the 3 amounts sum up to 1, and each person feels that they got the best deal. Formally, we are looking for an envy-free rent division. Now the division here comes with two things. One is the assignment to the room, and the other is the price tag of the room. Okay? That's the allocation of any person. And our task is to figure out if that is possible, and if so, are there algorithms for achieving that? So once again, let's try to understand the geometric space without worrying about the fairness. So let's say these are the 3 rooms, and say the rent for first room is P1, rent is this is P2 and P3. And the constraints are going to look very similar to what we had for cakes, that first of all, no one should be paid to live in a room. They should pay from their pocket. Okay, so the rent should be non-negative, and they should sum up to 1. And if you replace these things by x1, x2, x3, we've already seen that. So the space of the rents looks exactly like the space of all the connected cake divisions. So this configuration means that the rent for room 1 is 1 and the other rooms are free. Okay, and so on. And all other rent assignments are somewhere here. Yes? Okay. And once again, we can start by triangulating the space, assigning owners in a copy, asking them questions that at a particular price configuration means that room 1 is for P1, room 2 is for P2, room 3 is for P3. Which room do you like the best? Okay, so I'm going to assume that players have the ability to answer that question. And instead of the hungriness assumption, I'm going to assume that players are cheapskates. They would prefer a free room over a non-free room, regardless of how the room is. Okay, they're basically grad students, I think. So here are the assumptions. Ability to answer, or ability to pick a favorite room given any price configuration, and free room is better than non-free room. Free as in terms of prices. Okay. These are the assumptions on the preferences of the agents or the 3 friends. And let's repeat the exercise. So here are the 2 copies. Let me triangulate them the same way. Once again, assign the owners. So the 3 friends are A, B, C. Basically repeating what I did there. Right? For each of these price configurations, I'm going to ask the owner of that vertex, which room do you prefer? The rooms are numbered 1, 2, and 3. So how do the labelings look like now? What about the extreme vertex here, this one? So this means that room 1 is available at price 1 at a rent of 1, and room 2 and 3 are free. So What is C going to answer? 2 or 3? Definitely not 1. Similarly, A is going to answer 1 or 3. Yes? And we can fill the rest of the thing up. So this is 1 or 2. What about the stuff on the boundary here? Anybody? Yeah? 1 for every single one of these. Why? That's the only free room. 1 only. What about here? Okay. So that's a bummer. That looks nothing like Sperner. So what should we do? Can we prove that there still exists a fully labeled elementary triangle? Okay, so let's take the simplest step forward. Let's do case analysis. Okay, there's a bunch of OR constraints here. Let's go through them one by one. How bad can it be? Let's look at this vertex here. Say this is 1. We know that all of these things are 1. Yes? And all of these things are 2. Agreed? So what do we do now? So I understand that this looks nothing like Sperner, but does it serve the same purpose as Sperner? So let's think of, once again, let's try to redo the proof by walking. Okay. Once again, think of the 1, 2 edges as doors. Now, where are the doors here on the boundary? Anything else? Can there be any other door, no matter how I triangulate it? No, right? Because everything here is 1. This cannot be a 2, and everything here is 3. So if a 1-2 door has to occur, assuming this vertex is 1, it has to be this one, because everything further forward is only 2s, right? All right. Say we start walking. I mean, what the hell? Why?
Options of having 1 or 2 at the corner edges, but this is a special case.
This is a special case because the boundary has an odd number, like 1 is a special odd number. So it does have an odd number of doors, exactly 1 door. Let's start walking through that. Why not? Yes? Note that the property that we discussed, that any room has either 0, 1 or 2 doors, that has got nothing to do with Sperner coloring. It's a property of triangles. Okay? So any rooms here still has 0, 1 or 2 doors. Okay? Let's start walking. We enter a room. Okay? Maybe you pass through a few rooms. If you hit the right room, that's great. Is it possible that you can be thrown out of this? No, because this is the only door. So any walk that begins here is bound to succeed. Right? In the Sperner's lemma case and in the cake cutting, it was possible that when we enter through a boundary door, maybe we're thrown out and we can enter through another door again. But right now, for this, there's exactly one boundary door. Right? No question of failure. So basically, you'll have to repeat the proof that we did for Sperner's. And you can see that there's a fully labeled triangle. So, okay, this was all for the case where this vertex was 1. What if this vertex is a 2? Then this becomes the door, right? And repeat. Either way, you're bound to succeed. Yes? Okay, so what does that mean? That means that there exists 3 nearby price configurations where different people prefer different rooms. Okay? Once again, you can make the triangulations as fine as you want, compute an approximate rent division, and if you want exact rent division, make a closeness assumption. At least you can get existence of that rent division. Everybody with me so far? Okay. So fully labeled. Yeah, so there are many different ways of finding a fully labeled triangle. Yeah, I can give you like 3 proofs of that. One proof is by case analysis. The other thing is, this is actually called a dual Sperner labeling. So for Sperner, we had a fixed choice here and an OR choice here. For this labeling, you have an OR choice here and a fixed choice here. So if you, in a way, if you transform edges to vertices and vertices to edges, you just have to do a dualization. Okay, and if you want to read more about that, again, refer to Su's paper. He explains it very well. There's another wacky proof of this, which actually boils down to what I've done here. So let me just draw it on top of this, since you asked. So say we are working with this kind of a labeling. I can add some dummy vertices here, here, and here. Okay, like far away. And like they're like really far away. I mean, I can't even like draw them. So the reason I say that they're really far away is because there's this big triangle. So these are like straight lines, but I can't draw them because I mean I'm a finite human being. So so think of this as like a really big triangle that encloses this. And now I'm going to connect this exterior vertex with each of the points here. What I'm trying to do is I'm trying to create an honest to goodness Sperner labeling out of this. So I have to create like a meta triangle in which this thing is embedded. And you connect this, and you connect this third vertex to everything on this edge. Okay? And all of these things are like straight lines. So this, and this is a legitimate triangle. It just doesn't look like it. It looks like hyperbolic geometry at the moment, but this is a triangle. Now what you can do is assign labels. So the side where you have a 1 only condition, assign the extreme vertex in that side as 1, the extreme vertex here as 2, extreme vertex here as 3. And now this is a Sperner's triangle with no boundary vertices. Okay, so you just start walking through a 1, 2 edge, right? Because that's the only door that you have. And if you do that, then you'll realize that this thing really boils down to that case analysis that we just did. So it's not as, I mean, we're not doing brute force. It's actually a legitimate Sperner's walk. We are just thinking of it in a different way. Yeah. Nick, how much time do I have? Do I have any time left? 15 minutes? I was hoping to sort of show that app, New York Times article app. Anyway, I can connect my laptop to the projector, or I just need a browser. So I just want to show you a nice app for computing NV-free rent divisions that was featured in a New York Times article, of all places. It's pretty cool. You should play with it. It's quite nifty. Whoa, whoa, whoa. What? Stop. Oh, okay. New York Times rent division, yes. By the way, this link is again on the web page, so you don't have to like write down anything. No. Wait. I think it moved to a different window. You should go back to this window. This one. Waiting. Yeah. I think the password didn't work. Yes. Yeah, I think it should work now. Yes. This one. Let's go back to the article. Yeah. This one. Yeah. I think I'll manage. Yeah. Thank you. Okay, so I'll just take a couple more minutes to. So there's this article in the New York Times on rent division, and they have some really nice graphics, and they also have a rent division calculator. So you should go back and check it out. But this is the object that I was talking about. Okay, so you have these rent configurations. So the roommates' names are. I'm not sure if people can see it. Can everyone see what's written here? Okay, if not, please feel free to come forward. Uh, so the friends' names are Ashwin, Britt, and Chad. And for example, at this point, Chad picked room 2 because it's free, right? At an intermediate point, the rooms are priced at $750, $750, and $1,500, and Chad picked room 1. Okay, and so on. For each of these vertices, you can pick something, and you can make this finer and finer by refining this triangulation. And so look at this. Let's look at let's look at this white triangle in the middle. The rent divisions here are, look at the numbers for the rooms. They are super close, right? And you can make them as close as you want. So this was just a graphic, but they also have a rent division calculator. So you put in the total rent, say $1,000. Say there's 3 friends, okay, and so their names are A, B, and C. Your rooms are 1, 2, and 3, and you start the division. Okay, and the questions that it will ask is that it will ask roommate C, at these price configurations for these rooms, which one do you like the best? So maybe I say that I like room 2 at $500 the best among all these three. Then it will ask me some other question, I answer, then it moves to a different roommate, maybe a different vertex where the owner changes, and so on. It keeps asking you these questions. Let me go for the cheapest rooms. So, and after a certain point, this procedure stops. So again, this is a bounded protocol because you are the one who decides the triangulation, but it might not be like a polynomial query protocol. It might need to query every vertex in the worst case. So, and at some point it gives this room assignment at these numbers, and these are within $62.5 of fare, and that's the width of the triangulation. Okay, so it's just outputting one of the vertices of the colorful, of the fully labeled elementary triangle that we got. And the great thing about this is that you can continue dividing. Okay, so this was for a fixed refinement of the triangulation. If you want more precision here, you can continue. It is now going to proceed on an even finely divided triangulation on top of what you have already given. Okay, it is going to go on forever. So let's just do it for maybe one more time. You continue the division. Now say, now it gives you a somewhat better estimate of fairness. Okay, and you can play with it all day long. Okay, so and this is basically the history of all the answers here. So do go back and try to play with it and try to pay attention to these numbers. Try to follow the trajectory of the queries made by the algorithm, and you'll learn something interesting about the underlying algorithm that is that runs through this app. So it's a fun exercise. That is pretty much all I had to say for this. Let's meet up after lunch for indivisible words. Okay, great, thanks.